Okay, so we've got a gas in here, and this gas is going to exert a restoring force or something like that. So we press this piston, and this is frictionless. So when we do that, this thing oscillates back and forth. Okay, define simple harmonic motion as applied to P. Well, what we'd have to do, I guess we'd have to say either it's moving under the influence of a restoring force, which, by the way, is not in the Mark scheme. What they say is that the acceleration is proportional to minus kx. Okay, that if you drew a graph of acceleration versus x, right, it would be a slope like this. It would go through zero, by the way. Here's x, here's a. Okay, that the acceleration, I always think of it in terms of a force, right? The force is toward equilibrium. So here's your equilibrium point. The force is always toward equilibrium and proportional to x, which is of course true of the acceleration. So I don't know. Yeah. All right. Hope that helped. Try to determine it or explain it in terms of the acceleration of the object. Okay. The acceleration is toward equilibrium and proportional to the distance you are from equilibrium. Okay. Let's go to the next page here. It's always a good plan. Let's see. The graph shows how the displacement varies with time t. So this is like one of those cosine graphs, right? State the value of the displacement a as defined in part A, okay, which is this thing. That's just the amplitude, so let's take a look at this. What's our amplitude? 12, right? Just read that off the graph there. On the graph, use the letter m and point where the magnitude of the acceleration is a maximum. Well, the acceleration is opposite of omega squared x, right? So wherever x is a maximum, this is a maximum, right? So there it's a maximum, any maxima or minima in this case, right? They say maximum though. Do you suppose they discriminate between this and this? I don't even know. Okay. I guess you'll find out when you look at the mark scheme. Or the they say magnitude. So magnitude just means how big it is. So any of these extremes is going to be a maximum acceleration. That's simply because the spring is the most stretched out. It's exerting the most force at the extremes, right? Okay. Determine, using the answer from the graph and your answer to B letter I, the magnitude of the maximum acceleration of P. Okay. What I did was I just used this. I actually used this formula. So A is the absolute value of A, which is the magnitude, right, is omega squared x, right? So the maximum one would be the maximum x. So use this value. Notice it's centimeters, so turn it into meters and plug that in there. What do we do for omega? Omega is going to be 2 pi over t, and your period appears to be, what is that? Oh, about 0.04, right? That's 0.05, 0.01, 0.02, 0.03, 0.04. So plug that in for t, right? You can find omega, you can square omega, multiply by this. You're going to get a big number. It's a big acceleration. It's on the order of 3,000 meters per second squared, okay? Just saying, don't freak out. All right, the mass of P is 0.32 kilograms. Determine the kinetic energy at 0.52 seconds. So here's 0.5, and then this is 0.06, 0.07, 0.08, 0.09, 0.1, right? So every two of these is, okay, where are we? I think, so what you're going to do is just read this off of here. I thought that it was about here. Or here, somewhere in there. So read off what you think that x is, okay? So x is going to be something, right? Determine the kinetic energy. Well, you can use the kinetic energy formula, the fancy one, 1/2 m omega squared x naught squared minus x squared, okay? So whatever you read, whatever you think this is, that you're going to plug in for that. whatever this is, you're going to plug that x in for this. The mass is 0.32, so plug that in there. And then omega is going to be 2 pi over t. So figure out what this period is, right? What is that? That's your period, okay? Plug that guy into this, okay? You're going to get a number between, well, I got a number between 50 and 60 because I read this as 3. Looking at it now, I don't know. I think 3 is pretty close, okay? I think 4 is too low. But anyway, 0.52. You know, it's like, how carefully can you read the graph? All right.